Voyager 1 launched in 1977. Its power fades every year. Its computers are older than the engineers running them. In 2023, it went silent, spitting out nonsense for 5 months straight. Engineers fixed a 1970s chip from 30 billion miles away, with no way to touch it. Then the readings started arriving. What they found does not match the models. Voyager 1 launched on September 5, 1977, less than a month after its twin, Voyager 2, left the same launch pad. Both were built to fly past Jupiter and Saturn, take pictures, and gather data no human instrument had ever collected up close. Voyager 1 did its job and kept going, riding its own momentum straight out of the solar system. On August 25, 2012, it crossed a boundary called the heliopause, the edge of the bubble of solar wind our sun blows out into space. That made it the first human-made object in history to reach interstellar space, the region between the stars. It is still out there today, still moving, still transmitting. As of 2026, Voyager 1 sits roughly 15.8 billion miles from Earth, about 25.5 billion kilometers, moving away at around 17 kilometers every second. In November 2026, it will cross a new marker. A radio signal traveling at the speed of light will need a full 24 hours just to reach it, meaning a message sent on a Monday morning gets its answer back on Wednesday. That growing wait is only going to get longer, and it is already running straight into a much bigger problem the spacecraft cannot outrun. Voyager 1 does not run on solar panels. Out past Jupiter, sunlight is too weak to power anything useful. So both Voyagers carry generators that turn heat from decaying plutonium into electricity. At launch, that system produced about 470 watts, roughly what a couple of light bulbs use. That number has fallen every year since, by about 4 watts annually, because the plutonium naturally decays and gives off less heat over time. Today, Voyager 1 produces somewhere around 250 watts total. Engineers at NASA's Jet Propulsion Laboratory have spent decades managing that shrinking budget by shutting down heaters and instruments one at a time, in a specific order meant to keep the spacecraft alive as long as possible. The probe launched with 11 scientific instruments. By April 2026, only 2 were still switched on, the magnetometer and the plasma wave subsystem, after the cosmic ray subsystem went dark in February 2025. And the low energy charged particle instrument followed in April 2026. Engineers recently shut off yet another instrument to save power, hoping to buy enough time for an upgrade nicknamed the Big Bang, which could stretch the mission further and possibly even bring some instruments back online. That power fight has been going on quietly for years. But in late 2023, an entirely different kind of problem showed up. One that had nothing to do with power and everything to do with the spacecraft simply losing its mind. On November 14th, 2023, Voyager 1 started sending home data that meant nothing. Instead of readable science and engineering information, Mission Control got a steady stream of gibberish, described by NASA as a repeating pattern of ones and zeros, similar to a stuck dial tone. The spacecraft was still alive. Engineers could tell it was receiving commands and operating normally in every other sense. But whatever it tried to say back to Earth came out scrambled month after month with no obvious explanation. This was not Voyager 1's first breakdown. Back in May 2022, a separate system that handles orientation data started sending nonsense too, and engineers fixed that one by rerouting the information through a different onboard computer. This new problem was worse, and it took much longer to crack. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously. For 5 months, NASA had a working spacecraft that could no longer speak in any language anyone on Earth could understand, which set off one of the strangest repair jobs in the history of space exploration. The garbled data pointed engineers toward a part of Voyager 1 called the Flight Data Subsystem, or FDS, one of 3 onboard computers built by General Electric back in the 1970s. Its entire job is to take readings from instruments and health sensors and package them into one signal for the radio to send home. On March 3, 2024, engineers sent Voyager 1 something they called a poke, a command meant to force the FDS to try a different internal process and, hopefully, reveal what had gone wrong. The response was a complete memory dump, a readout of everything stored inside that computer. That readout showed about 3% of the FDS memory had been corrupted. Engineers traced the damage to a single chip responsible for storing part of that memory. NASA could not say for certain why the chip failed. It may have been struck by a fast-moving energetic particle from space, or it may have simply worn out after operating non-stop for 46 years. There was no way to send a technician out to check. That left the team with a strange kind of puzzle. They knew exactly which chip had failed and exactly what code it used to hold. What they did not have was any way to physically touch it, which meant the fix would have to happen entirely through software sent across billions of miles. The lost code could not simply be moved to one open spot in memory because no single free section was large enough to hold all of it. Instead, engineers broke the code into smaller pieces, adjusted them so they would still work as one connected program, and tucked those pieces into scattered gaps across the FDS memory. They started with the code responsible for packaging engineering data, the basic health information that tells the team how the spacecraft is doing. That relocated code was sent up on April 18, 2024, with a round trip of nearly 2 full days at that distance. The team had to wait and hope. On April 20th, 2024, confirmation came back. The fix had worked. Voyager 1 was making sense again. Over the following weeks, engineers repeated the same process for the remaining damaged sections, including the code needed to bring back real science data from the 4 instruments still running at the time. Project scientist Linda Spilker later described the process as something close to an archaeological dig, with engineers combing through decades-old memos just to remember how pieces of the 1970s hardware were originally built. That patchwork fix kept the spacecraft alive, and it kept sending back information from a part of space that was already refusing to behave the way scientists expected. Long before the 2023 breakdown, Voyager 1 had already reshaped what scientists thought they knew about the region beyond our solar system. Interstellar space is often pictured as almost completely empty. Voyager 1 showed it is not empty in the way most people imagine. It is filled with an extremely thin, electrically charged gas called plasma. Voyager 1 does not carry a working plasma sensor that can directly measure that gas around it. Instead, scientists rely on an instrument called the Plasma Wave Subsystem, connected to 2 long antennas that stick out behind the spacecraft like a pair of rabbit ears. When plasma vibrates, it produces oscillations that this instrument can pick up as a kind of tone, and the pitch of that tone reveals how dense the plasma is. In March 2012, a burst of solar wind and magnetic energy erupted from the sun. It took 13 months to cross the huge distance to Voyager 1, arriving in April 2013. When it hit, the plasma around the spacecraft rang out like a plucked string, at a pitch that matched almost exactly what scientists expected for true interstellar space. That single event became the strongest piece of evidence that Voyager 1 truly had crossed the heliopause the year before. That measurement should have settled the matter and moved on to the next chapter. Instead, it opened up a new question that scientists are still arguing about today. Based on earlier models, scientists expected the density of plasma in interstellar space to jump once at the heliopause, then settle into a fairly steady number, somewhere around 0.037 electrons per cubic centimeter on average across the wider interstellar medium. Voyager 1's first clear reading in 2013 came in at about 0.08, already on the high side, but explainable as local variation. The trouble is that the number did not stay flat. It kept climbing. Voyager 2, which took a completely different route, passed the outer planets before crossing the heliopause in November 2018, gave scientists a second data point to compare. By June 2019, Voyager 2 measured a density of about 0.12 electrons per cubic centimeter, a sharper jump than Voyager 1 had shown at a similar distance. Scientists have started calling this rising trend a heliospheric boundary layer, a kind of thickened zone just outside the heliopause where density keeps building rather than leveling off the way older models assumed. One idea is that interstellar magnetic field lines get stretched and strengthened as they wrap around the outside of our sun's bubble, which could squeeze and reshape the plasma in that region. Nobody has confirmed exactly why it is happening. That climbing density turned out to be only one part of the puzzle. A second Voyager 1 discovery involving something far more basic than plasma density turned out to be even harder to explain. When Voyager 1 first showed signs of leaving the solar system back in 2012, scientists expected one very specific, very simple confirmation: a change in the direction of the magnetic field around it. Inside the heliosphere, the magnetic field follows a spiral pattern shaped by the sun's rotation. Interstellar space should have its own, differently angled field, so crossing the boundary should make that direction visibly shift. It did not, even after cosmic ray levels jumped and the particles typical of the solar bubble disappeared, both signs pointing toward interstellar space. The magnetic field direction stayed almost exactly the same as it had been inside the heliosphere. For a while, that single detail made some scientists doubt Voyager 1 had actually left at all. Eventually, the plasma oscillation data settled the debate in favor of an interstellar crossing. But the direction of that magnetic field still has not lined up the way early models predicted it should. And scientists have never produced a fully agreed upon explanation for why the solar and interstellar fields would happen to point almost the same way at that particular spot. That unresolved compass problem sits alongside a third mystery, one buried not in plasma or magnetism, but in the raw particle counts streaming past the spacecraft. Cosmic rays are fast-moving particles that come from deep in the galaxy, often traced back to distant supernova explosions. Inside the heliosphere, the sun's own particles and magnetic field partly block these rays from reaching in. Once Voyager 1 crossed the heliopause, cosmic ray counts jumped sharply and then held roughly steady, exactly as expected for a spacecraft now sitting in open interstellar space. Except the details underneath that steady average turned out to be anything but steady. Scientists studying the data found sudden intensity increases at specific distances, one at about 111 astronomical units from the Sun, and another later at about 116.6 astronomical units, each arriving over a period of just days to weeks, rather than gradually over months. Alongside those jumps, the rate at which particle counts changed with distance, called the radial gradient, shifted abruptly too, then settled into a new stable pattern until the next jump. Researchers also found an unexpected imbalance in how particles were arriving from different directions relative to the local magnetic field, something a simple, uniform interstellar medium should not produce. Put together, these findings suggest the region just beyond our solar system is not one smooth, uniform zone at all, but something built from separate layers or patches, each with its own particle behavior. None of this was in the original plan when Voyager 1 launched in 1977 to study Jupiter and Saturn up close. It became an accidental explorer of a region nobody had built instruments specifically to study, and that accident is exactly why the picture keeps getting more complicated instead of simpler. Here is the honest answer, and it matters to say it plainly. As of 2026, nobody has a complete explanation for what Voyager 1 is finding beyond the edge of our solar system. What scientists have instead is a growing list of measurements that do not fit cleanly into the models built before Voyager 1 ever got there. A plasma density that keeps rising instead of leveling off. A magnetic field that refused to change direction the way it was supposed to. And cosmic ray patterns that jump and shift at specific distances rather than smoothing out evenly. That is not confusion for the sake of confusion. It is what real exploration looks like when a spacecraft finally reaches a place no instrument has ever measured directly before. Every one of these oddities has proposed explanations, stretched and compressed magnetic field lines, layered boundary structures, local pockets of turbulence left over from the sun's own passage through the galaxy. None of those explanations have been fully proven yet. The only way to settle any of it for certain would be more spacecraft built specifically for this environment, something that does not currently exist and is not funded to exist anytime soon. Until then, Voyager 1 remains the only direct witness humanity has to this region, even as its own power supply keeps ticking down towards zero. Voyager 1 is not simply an old spacecraft still limping along past its expiration date. It survived a 5-month breakdown that should have ended the mission, got patched back to life through software rewritten from 30 billion miles away, and kept collecting data the entire time that continues to contradict the models scientists built before it ever reached interstellar space. Current estimates from the Jet Propulsion Laboratory suggest Voyager 1 can keep functioning into the early 2030s before its shrinking power supply drops below the level needed to run anything at all. Before that happens, in November 2026, it will cross the 1 light day mark, a distance so vast that a simple good morning message and its reply will take 2 full days round trip. Whatever Voyager 1 finds between now and the day it finally goes quiet for good, it will keep doing what it has been doing since 2012, handing scientists numbers from a place nobody has ever measured up close before. Numbers that so far have refused to behave exactly the way anyone predicted they would. If you enjoyed this video, make sure to subscribe, and I'll see you in the next one.